also can improve the spectral efficiency of telepathic communication, but because huge number consume a lot of energy. To overcome this problem, general spatial modulation can simultaneously reduce the RF gain and still it keep maintain the spectral efficiency still high. General spatial modulation is based on spatial modulation. The idea of spatial modulation is we have multiple antenna. For example, here I have 4 antenna that is can convey 2 bits of each antenna. So because this is I use spatial domain, so this is the X01 and 11 can activate antenna B, and then from that antenna I can transmit 11 digital modulation from antenna B. But in spatial modulation, the RF gain is become small. It means the energy efficiency is good, and in the receiver side, it's easy to overtake interchannel interference. But for this spatial modulation, have a limit. The limit is if the spatial information is only grow with log 2 of number of antenna. So for example, if we have 32 antenna, we only have 5 bits to convey the spatial bits. If we have 16 antenna, only 4 bits. So this is the limit. To overcome this problem, generous spatial modulation was proposed in 2008. The idea is almost same like spatial modulation, but we activate multiple antenna. So the number of combination can be higher. For example, if we have 5 antenna and we activate 8 combination. But previously, if we use spatial modulation, we have 5 antenna, so it's limited. And then the idea is almost same. If we have information 10, 01, and 11, and the first 2 bits is denote the antenna combination. For example, here, see, 10 is antenna. So we can activate that antenna, and from that antenna, we can transmit the signal to the receiver. So here the number of bits is increased, especially for spatial. And then this is the system model of general spatial modulation that proposed in 2008. We have NT as transmit antenna, and R as passive antenna, NP is active antenna, N is antenna combination, and M is equal to modulation. Here we have B bits information. We have B bit information. B bit is containing L1 and L2. L1 is bit for transmit antenna mapping, that is for spatial domain, and then the remaining bit is for constellation mapping. And N is to the power of L1. That L1 is number of bits. So this is the combination of antenna. In the receiver side, we have multiplication between general matrix plus noise, and also it's equal to Hi times S plus noise. I is denoting the antenna combination. So here we have N antenna combination vector, not transmit, only symbol, active symbol. But for general modulation, there is a new problem. The new problem is in the receiver side, the receiver have inter-antenna interference. So how to decoding it? There is several methods. The idea of maximum magnitude is looking all the combination. For example, here we have 2 to the power of b comparison. So we're looking for the minimum distance. And then this is linear detector. The idea of linear detector is come from this equation. This equation is channel and transmit vector times plus noise equal to y. The idea is we put this as the inverse so we can estimate the transmit vector. For zero forcing, they have this inverse. So the inverse times y. But because we know here there is noise if close to zero, so the noise term will increase. So to overcome that, minimum mean square include the power noise term. So this estimation theoretically is better. But another problem is come. This only works is the general matrix F rho is greater than column. So it means if the receiver size is smaller than transmitter size, this cannot be equal. As we know, in generalized spatial modulation, number of active antenna, number of transmit antenna is greater than receive antenna. So, because of that, block linear detector can be solution. There is also same, but here we include I term that stands for antenna combination. So the equation is also same, but we only take the active column. So the name of this is block linear detector. It means for every estimation we have n combination and solution. And then, because we have n solution, we have to looking which one have minimum distance. So we do this n times and get the best result. And then now we move to
you say we call this lab.
for example, we have this term, but I, as we know, I is from 1 to n. From 1 to n. And then, for example, we have circuit combination. We make order from the minimum 1, and then from that one, we try 1. Is this fulfill with the edge? If no, go down, go down, go down. OBMMSE is good if only the combination of antenna is much. But if less, the cost for make order, mathematical cost to make order is high. So the idea is almost same, but this is the all combination of n. So of course, for the result between this and MMSE, this one is better than OBMMSE because it's try n combination. But for the time perspective, if number of MMSE is good in terms of neuron is kind of mathematical function. It's take one or more input that are multiplied by the value of weight. So that is multiplied with weight. So we can get sigma, and then this value passed to nonlinear function that determine whether the output will on or off. This is the Rosenberg model of the activation function, unit step function. For example, here is the value of sigma, where sigma is equal to W transpose Z plus P. P is bias. If the output of sigma is greater than 0, so the output is 1 and 0 for otherwise. And then this is variation of activation function. We have sigma, non-value, and value, and so on. But the idea is same. We can make a decision whether this is on or off. Some of function have a limit, for example, from 0 to 1, from -1 to 1, but value Usually, nowadays, we value for the activation. Why is that? I will explain later in the next slide. And then previously, I have already explained about a neuron. If we gather a lot of neurons and then make interconnection between them, we can call it multi-layer perceptron, which is multi-layer network. The output of Y is almost same like previously, and but we have factorized them like this. For example, Y hat is equal to activation function of W times H, W3 times H plus bias in this side, in Y side. And then we get the output almost same in H2 and H1. So this is kind of composite function. And then to get the better performance, we have to do learning. Especially this is supervised learning. In supervised learning, the difference between prediction value Y hat and the level or actual value Y is called error. We can use the error value to calculate the loss function LT. The purpose of learning is to minimize the loss function, so we can get the high accuracy. To minimize the loss function, we have a lot of ways. One of the method is using stochastic gradient descent. Can be expressed as next W is equal to present W minus learning rate times differentiate of L divided by differentiate of present W. This process is repeated until convergence. And before I learn about AI, I thought AI is new technology. When I first learned, I just know that AI is not from 1940. It was purpose in 1940, and then 20 years after that, there is a deep neural network. And 2 decades after that, the first neural network application was proposed that named is VNet that recognizes the digit. It can help us for detecting money, for example. And 1 decade after that, hardware for neural networks was proposed. As we know, the function of is kind of linear algebra doing multiplication, addition. So that's why we need a specific hardware to make the performance of neural network is better. But between 1990 and 2010s, AI didn't have significant change. But after that, the change is very much. Like we have Ujian or AlexNet that can fit and craft human model and so on. Why is that? It is because of 3 factors. The first factor is because of huge number of data available. For example, every day we using Google or YouTube. If we could using Google and type something, for example, we're looking for new bicycle, and then we go to Facebook, the sponsor of bicycle is coming to our Facebook. This is because of, and also every hour, every minute in YouTube, there is 500 hours video uploaded. So this is good for AI, for training, looking for big data. And then the second factor, this is very important about the improvement of computing architecture available in neural networks. Previously, when first computer came, they have CPU, central processing unit, that have arithmetic LU, and logic and memory. And then the idea of CPU is process general purpose application, and then process 10 operations per cycle. The purpose is for complex manipulation for a small set of data. Another one is CPU. CPU is then for graphic processing unit. But in 2008, NVIDIA introduced about using CPU as this because of frameworks. So it's make the developer is easy to develop this. So this is the system model of BDNN. BDNN is block deep neural network detector for GSM. It is almost same like conventional GSM, but here we have feature vector generator and FFDNN, required DNN. The basic signal is almost same. It's X plus noise, and it's equal to HI S plus noise. But here, because we have block term is mean we're looking for the active antenna. So we have the input for the neural network is Y and HI, where I, F, and matrix, the size is NR by NP.
I have a question. According to this slide, it seems that for the previous unit, we also do AI component for the GSM. But in structure, it seems that we use a single network for a single output bit. So these structures are independent.
Yeah, independent, right?
But for the previous one, status, they will pass a structure first and then divide it into several streams. So why do we need this and what's the difference between this? You know about this?
Yeah, no. Previously, I already used a lot of method, but this is I already tried and the performance is near for the ML. And then my friend also asked me, how do you do this? So I give him the code and also the explanation I explained to him. So he modified also. So this is my model. The idea is same, but I'm not using this. So from extraction, I directly do this.
Actually, I'm trying to say because in his model, the data will pass a connected network and then divided into several parts. But in your structure, you use a feature vector generator first. So is this identical to his structure?
Yeah, I will explain this in one slide after this about FET.
Do you know what I'm saying?
Yeah.
I mean, you have a feature vector generator, but he doesn't.
Yeah.
However, he has a structure, network structure in front of these individual branches.
Yeah.
So are these two the same?
I don't know. Yes, I'm not yet asked to him, but in neural network, each of neuron can only process real data. If directly put this data, complex data inside neural network, it cannot work. So neural network also it can work if the output is real, because this is complex number. So that's why we have to process here to make it real number pre-processing data. So if put directly, it's not works.
Okay.
Yeah.
I have a question. I look at your thesis. I think the output is not the output of the DNN might be SN.
Yeah.
So this is the difference between you and Yamaha's thesis.
Yeah. For this small BI.
So
Yeah.
BI is the
BI is okay. BI BI mean only bit. If you see, this is this one is SSV. This one is bit modulation. BI is for bit. Okay. But because we already select which antenna is active and which output, so we can produce BI fully like this. this model can predict this one.
Okay. So you mean the data, you mean the active antenna has been predicted previously?
No, the possibility. For example, here, this DNN is 2, 1, 2 together. And after that, I will explain later after this slide. There is explanation about this.
So here, the PI only indicates the bits transmitted by symbols.
Bit transmitted by transmit antenna, active transmit antenna.
I mean, it's carried by the modulation symbols.
Yeah. It is like that. This is the SFPG that I just heard about. We have to split the data because this is the complex number that cannot be processed in neural networks. So we have extract. I use SFPG. It stands for simple vector feature vector generator. That is, if we have each one split until H and R times NT. That is like that. It's easy. But because we do process in parallel, so each of TI we have put Y and HI, where I is indicate the active antenna. So from this TI, because I is from 1 to n, so each J time there is n combination of TI or vector input. And because we have ns time slot, so we can form our data into bit T is equal to T1 until Tns. The size of T is equal to NR plus 2NR and P. This is stand for the input size and multiply with N and Ns. And this indicate the number of possibility of
By Y into F. That's the, because the function. Okay, so
this one is
just factorize.
like this and become like this. The size is 2NR plus 2NR and P each of the I.
Well, NS J indicates what's
J indicates is time slot.
time.
Yeah. So N is stand for all the combination of TI. So each of time we have U1 to Tn, each of time slot, and because we have
So why you need to observe for NS time stop? Why you need to observe?
observation of observe. This is data.
But for different time slots, the data are not
Right, different slot. But during the transmission, I save the data until NS because this is the method for example, in aggregation time, we transmit 10 time slot, so we have NS is equal to 10 and so on. We get that first, and
my question is why you need to observe NS time slots?
yeah, that's why I will explain about the advert previously. But it's okay. The purpose is in GPU we can do parallelize, or in NN we can do parallelize. So the purpose is make it factorize first and put together into the NN. So the speed is become faster.
So this is only to increase the speed.
Yeah, because it can be parallelized. So gather the data first and put together.
Okay. So this is not for observing some feature. This is just for speeding up your structure.
Yeah, for computation, because the available hardware nowadays is like GPU, CPU, or SoC, even for
because you put it into feature factor
yeah.
generator, so that would lead to some misunderstanding. I thought you observe more time is because it can extract some features, but it's not.
So this is independent.
Okay.
And then after that, after putting in the NN, because this is parallel, we get P, is from P1 to PNS. So each of time slot, we can get the demodulation P. And then each time of each time slot, we have P1 until Pn. This is time for the combination antenna 1 until combination antenna n. So we have n solution. Since we have n solution, so we're looking for that is correct. So to looking for it, we can convert it into symbol, transition symbol, and multiply with hi that we already see previously, and we can get y I n. So we can looking for the minimum distance or of each time, so we can get I n, and we take I n as the solution. So we get solution, 3-bit solution of each time slot as the final output.
What is the relationship between y hat and the pi?
So in DNN we have encoder. In encoder, for example, we have P-bit. P-bit is meant for L1 plus L2. And then from this bit, we can convert into symbol. We can convert it into symbol from this, like in previous slide in our function is using value, and the function is like this, max 0, x. So if we derive this equation, the output will either 0 or 1. So for the network to back propagation is faster than the other. But if we use value, we usually use space normalization to make the output is, we can normalize the output. And then using STP for optimizer, and the function is cross entropy. And here, running rate 0.05, training set, in the training set 75%, and 25% for validation.
So I still think from page 20 to 21, but this is the you have a page number here, why you need to. I mean, page 20 to 21 is the
Second previous slide.
yeah. But page 20 and 21 is the core of your office.
Yeah.
I think you need to say for more detail because,
Okay.
for example, in 20, I have several questions. On page 20, the feature, you say the DI, the first time is the Y is the signal you receive at the J time slot, right?
Yeah.
And the other part is HII. You test here. You test only the first combination of the channel.
I combination of the well, I is from 1 to n.
Yeah. So this is actually the feature for the first DNN.
No, this is from first until the end.
Okay, what?
First until the end. So we have n combination of active antenna. For example,
I mean, DJ. Oh, okay. So you have tried. Oh, this is the first kind of combination.
yeah,
All kinds of here.
until the end.
Okay. So this is in your model. This so you feed these to this
yeah, I got the idea.
because in this figure, in the model, the figure you say D, and you have a subscription. What is this?
This is for item cloud. So I have to change to this.
So the entire D with the superscript DJ are submitted here.
No, that is actually this small d.
Small d.
Yeah.
So this is a typo.
Yeah.
Okay.
I have to
So
change that.
you only feed the small d into this
Yeah.
network, and for network you feed different things to next.
Yeah, because this is CPU that can do a lot of process. So I have to make DI, as we can see.
Okay, small d.
D is the size is DI size vector is row, the number of row of this, but we multiply and
Different information to different DNA.
yeah together.
Together, but different information, right?
Yeah.
D1, D2, and D2, D.
Yeah, until n and ns.
Okay. So the y
Vector.
for the next page, the loss function, as Professor Wang said, you calculate this previous one.
Public is not do that. This one, that's not it.
No, just
Page
page
one.
So the y, this is the receive signal. So this is generated according to it is different in different network, right?
Yeah.
According to the active pattern.
Yeah, it's different. Because we have encoded from data flow to symbol. For example, I have DI.
And so this is for this network is for a specific active pattern, right?
Yeah.
So the loss function calculated here is according the y hat is generated according to this kind of active pattern.
Yeah, y-hat is come from after we calculate and we get d as our bit. The size is 1 by d, where d is the length of bits. And then from this we can convert it the last L2 bit into S. S size is equal to complex number. The size is NP by 1. And then because we have a combination of I, so this is inside set of I. So for generating S hat, for generating Y hat, I is equal to HI line.
Okay,
SI.
I understand. So this means that for the page 31. So here is the way you determine which antenna to be activated, and for the bits, it's determined by what?
So as I mentioned before, the size of D is equal to Q. The size is 2. And R times plus and R and P times and S. So we have this vector, the row size is this, but the column is n and ns. Same like this. The size is n, p, and s. Why now become p? Because the output of this time, because each time is we have bit. So the output is B is like this. Yeah. This is n times, and this is the length of this is EB. So each time slot we have E hits time n of time slot. This happens until ENS. So we have n solution of each time. But for each time,
What I don't know is the actual algorithm. For example, are you determine this first and then go to that version to decide your transmitted bit through modulation symbols, or I don't know how you do the decisions.
the first is according to there also according to page 18, the output of the network is VI, is called VI.
Okay.
And then because we parallelize it, we have B, 1 until BNS, where B G is equal to this bit.
Yes.
And then as the output, we get bit first. And from this bit, we can do encoding to C. B size is equal to bill of 1 times B. B is equal to L1 plus L2. And from the L2 of each bit, we can convert it into SI. That's why I can convert this into YI.
Yes.
From SI to HI. So the order is like this. So after we convert this all to become YI, we looking for the distance between the receive signal and the prediction symbol predicting.
Okay, so then you determine the active pattern.
Then I can know which one is the
Yes.
solution.
Yeah, and then choose the corresponding B.
Yeah, become EI and put I with I hat. This is become solution.
So, I mean, the presentation is too brief because I don't understand and I need to read it myself so that, just let you know about this.
Then this is the parameter explained previously, and this is theoretical analysis of complexity in terms of MEC, multiplication and addition. That is, if we have two complex symbols, for example, this is A plus BI times C plus BI, we get this. This is for a value of multiplication and two value of addition. The way I calculate the complexity is like that. So this is multiplication addition. But for the type complexity is available in test book, I divide between addition and multiplication of each operation in each one. And this is the output of simulation, and we transmit antenna 4, receive antenna 2, and receive antenna 2 by employing QPSP. The result is, in terms of PDN, the performance of PDN is close to ML detector. And for 0 forcing plus 0 forcing and from MMSE, the performance is much worse than ML, PDN, and ML. But previously, I only ran for 3 layers. But in Friday, I do presentation in front of Professor Lee and Professor Jen. And because Professor asked, how about if we reduce the number of layers? And then I do, and the result is impressive. If only the question is come in last month, I will put in my paper this 2 layers because the performance is much better than 3 layers. Yeah, thank you for the question. So I can do this. So the computational complexity, the computational time higher than 3 layer, but it's okay. It's still our same.
This is for lower number of antenna. If we have higher number of NP and NR, so in that case, with lower layer, the performance will be worse than higher layer.
And this might be something we can discuss because there might be some sort of relations between the layer numbers and the antenna numbers. Total.
Because here the active antenna is only 2. Even if we increase the NP and NR, still the performance of 2 layer will be closer to 3 layer. Then the performance of 2 layer become worse than 3 layer
Because the number of active antenna is small. That's why 2 layer is still okay. And this is for another combination. NP is higher than previously. 16 transmit antenna, 2 active antenna, 4 receive antenna, and using QPSK. Same, the performance is almost same. For all, it's slightly same. And for the combination, VDN and 2 layer is much faster than VMNT, and then this is for the higher number of transmit antenna. We have NP is equal to 128, NP is 2, and R is 64. The performance is much better because in the receiver, because the transmitter is 2, the receiver is 4, no matter the number of transmit antenna is higher, but the performance of everything is become much better. So the SNR previously I ran from 0 to 24, but for this simulation, because number of NR is high, so I start from -20 because after -4, the performance is become drop.
Just a little bit curious that why, in the case that NT is equal to 4, why 0 forcing and FSC have bad performance? I mean, on page 24, the performance of 0 forcing and MMSC is pretty bad, but in this case, the NT just 4. Is this normal?
I'm not expect about that, but I think it's because of we have number of active antenna 2, number of receive antenna is 2 also. If we do pseudo inverse is different with inverse, right? So it's just estimation. So that's why the performance is
So this implies that you have a better advantage when the receiver antenna is equal or even less than the active one. So you need to explore this.
But if less, I already tried. For example, NP is 3 and R is 2. Everything works. No matter MMSE, DNN, and everything. But it seems it's still okay. My DNN is good. But for DNN and the MMSE, the 0% is worse.
Okay. Because I think your work is great, but maybe it's more can have more values if we discuss some critical issues. For example, in many GSM papers, they talk about when the active antenna is very large. Yeah, but not active, the total antenna is very large. You have only 4. They have already discussed. Oh, okay. Yeah, okay. And maybe for another cases that receive antenna is very much less than the total antenna. So maybe you can try some case.
Yeah, like it's practical, the number of NR usually is small. Previously, I already tried, of course, for smaller NR, because the input of DNN is even of Y and HI, where if the number of NR is small, it means the vector Y is small. So the input of DNN is not too much. So to extract that information is we have to do. But if number of NR is high, the number of filter can extract easier. this is the performance between modulation, showing. And then this is the comparison between PCNN and PDNN. Actually, I'm not proposing PDCNN. This is only for comparison. Can we do pattern extraction or pattern recognition in detection? Because as long as I know, CNN is work for detecting pattern. So the idea is almost same, but I put consolidation layer with maximum volume. Why the performance is not good? From my analysis, is because information in H and Y and H is independent, especially in H, because H is complex 0, 1, complex with complex value random. So it doesn't have pattern. So if we do maximum pooling, of course, some information is lost. But for example, CNN is work for like picture. For example, there is figure of human. After we do convolution and we extract, of course the size is small, but we can see maybe it can detect, oh, this is hand, this is foot, this is hand. But because this is complex value and this is random, if we do remove with maximum pooling, it will destroy the information. That's why the performance of when I put convolutional layer with this configuration, the performance of the CNN is not good. This is DNN ML. This is for DCNN. ML and DNN. This is DNN. DNN means before network without CNN. Because CNN is also kind of DNN. That is one. And then this is the for PR comparison between in NT and SNR. Of course, with higher number of NT, performance is become worse than PDR. But this is a trade-off, because if number of NT become higher, of course the number of element is become higher. So this means the data rate is increased. That's why the performance of PDR is become worse in higher NT. And then this is the feature works. We can extend this works to multi-user traveling GSM. I already tried, but using SVD recorder. So here the recorder is using SVD. As we know, for do estimation is SVD, it's still just x hat is equal to u Hermitian times with y. So we can get the estimation of signal. Yeah. Do like this, we can get estimation of signal. So that's why when I compare the output of multi-user that I have done previously, the performance of SVD is much better than DNN. Why this happen? Because in SVD, this is exact solution like closed form, but in DNN, because DNN is only approximation, so that's why the result is not good. For example, we do simple problem, A plus B. We using CPU to calculate this. Of course, this is exact solution. We have exact solution C. But if we put A plus B inside DNN, this is only to approximation. That's why the performance is not really good. And also the complexity, because the complexity of DNN is depend on how much the layer. So if we put a lot of layer, of course, this is slower, and also the solution is not exact, just approximation. So I will
I mean, this C.
are same because the problem is simple. For example, Wi-Fi, where I is for 1 to user A. Same further, the way we estimate is do like this. You have vision of user 1 time with the receive signal in this, for example, only one user. Same. So the solution is like this. But I forget to not to put the index. If I put the index, almost same. I'm not yet tried, but I think like that because this is only the number of users. And then another utilization of deep learning is for communication system is possible to adopt adaptive modulation scheme that the modulation of the will decrease in low accuracy. For example, I have base station. When I have base station, the weather is not good. There is rain. So because the base station know the weather is not good, so the base station can decrease the modulation order. And in the user mobile will check why now I'm not receiving the signal. So it starts to looking for adaptive modulation, change the modulation scan. And then, for example, previously we have 64 cup, but immediately in our phone it's lost the signal. And then because of that, our phone is looking for the lower constellation. After it matches, then receive the signal. So the adaptive modulation will stop and skip and do normal activity. So this is possible to put in later on in deep learning. And also a lot of paper already talk about adaptive modulation by using CNN. So it can detect the pattern of modulation but not demodulation. So the conclusion is through numerical result we verify that PAR performance of robust DNN SIM is better than 0% active DNN detection. Although the PAR performance of PDNN does not take away or perform the classical ML, of course, because ML is the optimal one, whereby the PAR of both SIM almost overlap. But in PDNN is built in terms of time execution than ML, but the result is almost same. Okay, thank you for your attention.
Can you go to page 9? Your method is to replace the block linear detector by neural network, right? Your method. So from your experiment results, you find the VR performance is better, and also the speed of the neural network is faster than the linear detector.
Yeah.
But why neural network is faster than the linear detector?
Yeah. Why neural network is faster than the linear detector? Because in linear detector we use multiplication and addition in complex terms, right? In complex domain. But in DNN, I extract this complex value into real value and then do multiplication and addition with a lot of data because in CPU can perform better complex manipulation but small set of data. That's why the operation is small. But in DNN, simple manipulation, that's why only a up manipulation, multiplication and addition, but with large numbers data offset. That's why I get the data first together and then put together the output is much faster than conventional mathematics. Of course, with different tools, different architecture. Why? Because nowadays the hardware, like previously, when I do my mini thesis in Indonesia, I have to choose whether my speed of signal processing is fast or accurate. So in that time, I have two options, fast or accurate. And then, because in multiprocessor, if we choose accurate, we do mathematics. At that time, I calculate sinus and cosinus term. If I use mathematics, it becomes accurate, but because the process mathematics in processor, in AVR processor, is the specification is not too high, so using mathematics is not good. So that's why the idea is I putting EPROM. EPROM is like static memory to put lookup table with some precision. The idea is still from the available of hardware, we can do modification, utilize it to perform a simple manipulation of real part. So you can compute with faster, much faster.
But this is the, this is the solution about hardware processing.
Yeah, this is every
So maybe character, maybe you can also use the same thing for computer processing.
but in linear predictor, it has complex number. I mean, complex operation. But in neural network, only multiplication, addition, real number.
But these, I think I see some detectors before they also complex number.
Maybe it is possible.
Yeah, I think it's possible. First of all, the question is that is it fair to do such kind of
Yeah, and I was before if you have different professor that
Yeah, that's why
maybe is it also in the paper you submit?
yeah.
Maybe there's possible some review
But the reviewer is often not about the comparison, because I also mentioned the specification of my time, and also I already mentioned the complexity in terms of time, and also the complexity in terms of mathematics. So everything is provided. Of course, in mathematics way, the computation, the mathematics of this is depend on delta K. If delta K is big, of course the computation mathematics is big. That's why, because the simple of DNN is using a real number that can execute easily in GPU or TPU.
So if you only look into the theoretical complexity.
Yeah, but this is the higher. Yeah, this is the higher.
but higher under specific conditions. If for higher number of NP, then number of complexity of
And also, if you see from the perspective of the performance of this is good, but in terms of complexity, this is relative. That's why I explained about the history of AI. This happened because of network. Because maybe we can imagine 5 years after this, because now the simple system on chip by using like AI processor, like Huawei NPU from getting and India. So this is happened because the available of network. Of course, the complexity is high.
And that makes sense. The complexity may be higher, but maybe you have some other solution to solve this problem.
Yeah, the available of network.
I have one more question. Given the try how many number of receiving antenna is needed to achieve satisfactory performance.
You know what is you have a certain QS is quality of service for every area. If you want to achieve that one, then how many minimum disability level you require?
Maybe we have to try, but this is what if and only if number of row is higher than column. It means number of NT is greater than NT, or because we activate the only consider the active antenna. So as long as the number of NT is smaller than NR, we can be good. But the performance we have to make QS like Dr. Sim said.
Maybe you can show one figure the relationship between this last region. Data is not that. So if you, for example, if you plot the 3D graph, so NT and P and NR, so you will find certain region with that specific antenna, so data you can achieve.
Have SNR, I fix the SNR, and I make a plot like this, three-dimensional plot. This is NT, this is NR. We fix the SNR so we can make a surface.
That would be a good.
You can try this.
Okay. Because actually I have but only in one dimension, like I showed before.
Maybe you can add this in the final version of Thesis.
Like in this result, but I only have one dimension. But if you push another axis, you can see.
And maybe follow the first question, and then you can add it to the final version.
So instead of plotting, just we will relate to it.